and just after we will have a session of comments and questions, and just after the deliberation. So first of all, I would like to present the members of the board. Alexis, so myself as the president, so Christine Campagne, I'm professor at ENSAIT. You have two reviewers. So the first one is Mrs. Diana GOLODNITSKY, professor at Tel Aviv University. Can you hear us?
Yes, I hear you very well. Thank you.
And the second reviewer is Mr. O'Dwyer, professor at University College located at Cork. Can you hear us?
Yes, I can hear everyone clearly.
Okay, thank you very much. Just after, we have three examiners now. So Mr. Eric McDonald, professor at Youngstown State University. Can you hear us?
Yes, perfectly. I wish I was there, but I can hear perfectly.
The second examiner is Mr. Michel Armand, Emeritus Research Director of CNRS of Picardie University. Can you hear us?
Yes.
Okay, thank you. Finally, the second examiner is Mr. Michel Armand. Sorry, Mrs. Sylvie Brujon. You are physically present here. She is a research engineer of Picardie University. And finally, your co-supervisor, Mr. Panier and Mr. Dupont. So to improve the quality of the connection, please can you switch off your microphone and maybe to cut your webcam. And when the presentation will be finished, you can switch on your microphone and your webcam, of course, as soon as you have to speak. Okay, so good afternoon, everyone. We are here today for the defense of Mr. Alexis MAUREL. So you have 45 minutes to present the research activity during your PhD. So I give you the floor.
Thank you very much. So good afternoon, everyone. It's a great honor for me to be here today. And in order to defend this PhD thesis, today my talk will be entitled Thermoplastic composite filaments formulation and septembre of a lithium-ion battery via fused deposition modeling. This PhD thesis was funded by the FEDER and by the region Hauts-de-France and supervised by Sylvie Brujon, Loïc Dupont from the laboratoire Réactivité Chimie des Solides, and from Stéphane Panier from the laboratoire de Technologie Innovantes. So today's presentation is going to be divided into 5 parts. First of all, after a brief reminder about the context of this thesis, I will enter into more details regarding the composite filament formulation as well as 3D printing of a complete lithium-ion battery. These 2 parts will be only focused on the liquid electrolyte technology. And thus the 4th part of this PhD thesis here of this presentation today will be about towards the solid state technology of a lithium-ion battery. And then finally, I will conclude and give you some perspective about this. So first of all, about the background of this PhD thesis. Nowadays, in 2020, we are 7.8 billion of people. And by the end of the century, as you can see here, it's going to keep the same or it's going to increase a lot. And so in parallel, if we plot at, if we take a look at the world energy demand, you can here see that the trend is increasing as well, right? And during the last decades, we heard a lot on the news actually about the rising environment concerns, okay, due to fossil fuels energy sources. And last decades, we saw as well some governments that tried to put some new regulations in order to implement energy transition. Here you can see actually in the graphs that since 2000, we can see that the part of renewable energy sources is increasing and increasing. About the main issue with these renewable energy sources, such as photovoltaic, for example, or wind turbines, here is that both techniques, both energy sources here are, for example, intermittent, okay? Intermittent energy sources. And so energy storage devices are mandatory in parallel. Among these energy storage devices, lithium-ion batteries are really well used nowadays due to their good cyclability, long cycle life, as well as good energy density and power. And so these tiny devices nowadays are really mainly used in many applications, such as electronics, home appliance, transports, and it's so used nowadays that actually the entire field was rewarded last year when the Nobel Prize in Chemistry was awarded. If you take a look at the commercial lithium-ion battery, first of all, you will see that it's based on the liquid electrolyte technology. And you have different components. So you have a positive electrodes, a negative electrodes, and they are both separated by an electronically insulator separator membrane. During charge, here you can see that the lithium-ion will move from the positive electrodes towards the negative one, while the electrons will move through the external surface. During discharge, as you can see here, the exact reverse phenomenon will take place. Now, if you take a look at the design of a commercial lithium-ion battery, it follows mainly a two-dimensional architecture. Indeed, it consists in some kind of booklet. So the pins are stacked or rolled, okay? And it was reported in literature in the past that if you move from a two-dimensional architecture of the battery toward a three-dimensional architecture of the battery, actually you can improve considerably the power performances. And here, as you can see, it's due to the increased electrochemically active surface area. Also, the lithium-ion diffusion is greatly improved thanks to this kind of architecture. So actually, this trend here was confirmed during this PhD thesis. We did modeling study here, and we compared some two-dimensional architectures of the battery with three-dimensional architectures. And so based on the results that I'm going to show here today, first of all, we saw that here you can see the lithium-ion diffusion path, and you can see that in a planar two-dimensional electrodes, two-dimensional battery system, here you can see that the lithium-ion are just moving in one dimension between the electrodes, so simply doing the shuttle. While in three-dimensional architectures of the battery, such as the gyroid here, you can clearly see that the lithium-ion will move towards the wall space in 3 dimensions. And so based on the results that I'm going to present today in this presentation and the results based on the thesis, we were able to model and simulate a Ragon plot, so energy density versus power density. And here, indeed, at high current density, so for power application, we were able to demonstrate that we have better performances for three-dimensional architectures compared to 2D ones. If we two-dimensional architectures, so it's classical, okay, but in order to reach three-dimensional architectures of the lithium-ion batteries, such as here the gyroid, for example, these geometries are so innovative actually that you can only obtain them with very innovative technology, such as 3D printing. There is another advantage of 3D printing actually, is that you can implement the wall battery into the wall object. Here is an example. If I took it as example that was done in literature by Kim and Hall, they took as example connected glasses. And here in connected glasses, commercial ones, you have the lithium-ion battery, which is a huge block on one side of the frame, as you can see. And thanks to 3D printing, we could really imagine to hide this wall lithium-ion battery to the wall frame of the object. So the battery will become the object. But what is 3D printing? 3D printing, we also call it, scientifically speaking, additive manufacturing. And it consists on consecutive layers of materials that are deposited on top of each other. So first, you need to draw the object you want to print, okay, thanks to computer design software, and you will obtain what we call a STL file, which consists in a mesh of dots, a mesh of triangles. Then this file will be sent to a software called a slicer, a second software, and here you will divide your object into horizontal slices. This is what we call a G-code file. Within this G-code file, here actually you will also implement printing parameters such as printing temperature, printing speed, etc. You send this file, this G-code file, to the 3D printer, and by pressing just the play button, you will be able to print your final object layer upon layer. Nowadays, the emerging 3D printing techniques in order to, that are used in order to print lithium-ion batteries are the following. So you have the liquid deposition modeling, also called direct infrared heating, top left video. You have also the selective laser sintering, which use powder. On top right, you have the FDM, the fused deposition modeling. And then you have also the stereolithography apparatus. So among these four techniques, the first step of this PhD thesis was to make the good choice, right? I mean, we needed to choose among these four processes, which process are we going to use to print lithium-ion batteries. And so here, right from the beginning, we decided to exclude from this thesis the selective laser sintering and the stereolithography apparatus. As with both techniques, actually, unfortunately, you cannot print multi-material objects, meaning that you can only print only one material at a time. Unfortunately, so with both techniques, you cannot imagine to print such gyroid architecture for the lithium-ion battery. While with liquid deposition modeling and fused deposition modeling, you can. So multi-material printing options are existing. So then, among these two techniques, LDM and FDM, we needed again to make a choice. And so we take a look at the advantage and drawbacks of each technique. And here, with liquid deposition modeling, actually you use an ink as material source for the 3D printer, so an ink or a slurry, solvent-based. And here the main issue is that first of all you need to make a post-processing step, okay, in order to remove the solvent, etc. But also here the viscosity is a major issue, and due to this viscosity of the slurry, actually you have some air limitation. So if you want to print a wall object, an object battery, as I was showing previously with the connected glasses, for example, here you will be somehow limited. So in this sense, we just decided to focus this PhD thesis on the fused deposition modeling. And here, because you don't have this A limitation and you don't have any post-processing. But here you have another drawback actually with the fused deposition modeling. You have a filament formulation that is mandatory. Indeed, if you take a look at the process itself, you can see that it uses thermoplastic filaments as material source for the 3D printer. This filament will be introduced within a heated nozzle, and by displacement of this nozzle into the three axes, X, Y, and Z, you will be able to print your wall objects layer after layer. So here are the challenges that we needed to address during this PhD thesis. So the first part of this PhD thesis was focused mainly on the composite filaments formulation, corresponding to each component of a classical lithium-ion battery using liquid electrolytes. And so in order to confer some mechanical strength to the filaments, we decided to use polylactic acid, PLA, as polymer matrix. Why PLA? Because first of all, this is a green polymer made from corn. And also PLA is actually the most used polymer for FDM applications. Concerning the electrochemical performances, we decided really to choose classical active materials such as graphite and lithium iron phosphate as active material for respectively the negative and the positive. Of course, it was a huge compromise that we needed to do between the mechanical performances on one side and also the electrochemical performances. And so if you have a filament, for example, with too high loading of active material, here you will clearly have some printability issues. While on the contrary, if you have not enough active material within your filament, then what you will be able to print will show poor electrochemical performance. So that was really a huge compromise. Finally, once you develop and you finish to develop these filaments, the main goal of this PhD thesis was here to print the complete lithium-ion battery in one single step. That was the main goal. So we started first of all with the composite filament formulation. First, we established an elaboration process. So here we decided to use a solvent in order to combine both polymer matrix and as well active materials. That was here not ideal, but at least it was easy. I mean, it was more easy to have homogeneous here samples at the laboratory scale. And so after that we have an homogeneous slurry, we perform tape casting, and we will obtain, after evaporation of the solvent, we will obtain a classic film. This film will be divided and cut into tiny pieces and will be used as a material source in order to feed the extruder. With this extruder, we will obtain then, after extrusion, a classical 1.75 millimeters filaments. This filament, finally, next step, will be used as material source for the 3D printer in order to print many objects, such as here, those 3D printed discs. So I would like to remind you that here at the beginning of this thesis, we just focused on the filament formulation regarding liquid electrolyte technology, okay? And first of all, we started by developing the filament for the negative electrodes. So before starting to develop this filament, actually, we just took a look at what was available on the market. And we see this filament here, a commercial filament that had 8% of graphene and 92% of PLA. Unfortunately, here, right from the beginning, we were thinking that 8% of graphene will be maybe a bit too low amount of active material in order to confer good electrochemical performance. And so, instead of using this filament, we decided to create our own filament. This filament, we tried to load a huge amount of active material. And here, as you can see, we tried to load up to 70% in weight percentage of graphite and only 30% of PLA. Of course, here the goal was to maximize the electrochemical performances while maintaining just enough mechanical strength in order to allow printability. So here, that was a huge amount of active material we tried to implement. So let's focus on this main filament that we try to do. So first step, of course, slurry. We combine polymer matrix and graphite here in solvent. Here we use dichloromethane. Then we obtain a film, and this film we cut into tiny pieces in order to feed an extruder. Unfortunately, the resulting filaments here, as you can see, was not printable at all. It was too brittle. And so we had an idea, and this idea was, why not try to incorporate a plasticizer in order to improve the flexibility of this filament and thus improve the printability. So again, starting from the exact same composition, okay, 30% of PLA and 70% of graphite, we tested different kinds of plasticizer, polyethylene glycol denatured 500 and 2000, acetyl tributyl citrate, and propylene carbonate. Here, when we try to make a filament with propylene carbonate, actually, as you can see by differential scanning calorimetry, we have a broad endothermal peak between 120 degrees and 250 degrees, and it corresponds actually to the evaporation of this propylene carbonate. And thus, it corresponds exactly to our observation. The filament that we obtained was really brittle and so not printable. So here we ruled out propylene carbonate as a plasticizer. Then we try to make a filament with ATBC and PGDME 2000. But unfortunately, after only a few days, the filament was really, really brittle. And actually, we saw some tiny drops on top of these filaments. Both plasticizers were actually exiting the filament, meaning that maybe there were like an incompatibility between the plasticizer and the polymer PLA matrix here. So again, we ruled out both plasticizers from this process. And finally, with PEG-DME 500, we didn't have any issue here. So we pursued our optimization and we tried to optimize this plasticizer content. We did a different composition, and by doing a printability test, but as well as a tensile strength test in order to determine the Young modulus, here we saw, thanks to the printability test, that if you have a filament with less than 20% of your plasticizer here, we got a filament that was really brittle. While if you have a filament with more than 50% of plasticizer, the filament was too flexible to be printed. And so here, finally, thanks to the printability test we have done, we conclude that the filament containing 40% of PEG-DME 500 was here, or optimized something. And it corresponds finally to this ratio here, so 27% of PLA, 62% of graphite, and 11% of this type of plasticizer. Of course, it was necessary to take a look at the filament homogeneity. So we have done that thanks to scanning electron microscopy. And so here, for the resulting optimized composition, actually, you can clearly see that the graphite weights are really well distributed into the PLA matrix. Nonetheless, it's really worth mentioning that in order to have such homogeneous sample, such homogeneous filament here, up to 100 grams of materials was required in order to ensure good homogeneity. And this is particularly time consuming. So from this optimized composition about the plasticizer, then we pursued our optimization and we try to implement some conductive additives such as a carbon black or carbon nanofiber in order to improve the electrical conductivity here. Of course, as it is a purely electronic conductor, we had, we had only classical Nyquist and Bode plots for corresponding to purely electronic conductor here, normal. So simple dots within the Nyquist plot and only horizontal lines in the Bode plot. And then we pursued our optimization. So we try to add some carbon nanofiber, we try to add some carbon black, and finally we reach our optimized value, which actually match the optimization that we have done thanks to the electrochemical characterization I will discuss later. Here is the optimized amount, the optimized ratio of the filament. So 33% of PLA, 49% of graphite, 5% of carbon black here, and 13% of PEG DME500. If you take a look at the TEM image, you can clearly see that the carbon black is really well distributed within the PLA matrix here. Again, so as I previously just mentioned a little bit, so we pursued with electrochemical characterization on both films and 3D printed discs. We have a small issue here. Okay, perfect. So we did electrochemical characterization on electrochemical characterization on both films and 3D printed discs. So here we cut as well some discs from the film, and we inserted those discs into a classical swing. So here we got our working electrode, and we tested that actually versus lithium metal. This is really classical. Then from this, we were able to check at the electrochemical performances. So for the films here, as you can see, with the optimized value, actually, we were almost reaching the theoretical capacity of graphite, the active materials, which is about 372 milliampere hours per gram. And so as we were reaching almost this theoretical value, then we tried to produce a filament, and then we printed some discs. These discs, again, were tested electrochemically. And so here, for the exact same composition, actually, you can see that we have a huge gap between what we obtained for the films and what we obtained for the 3D printed discs. And unfortunately, here, this gap is mainly due, and only due, I would say, to the difference in thickness. Indeed, with fused deposition modeling, you are subjected to a first layer resolution limitation. The first layer, when you print, you are subjected, the first layer will always be thicker, you will be always about 200, 250 microns, while the upper layer you could go down to 50 microns. So here we got this gap, but this is only due to this first layer resolution limitation. Finally, if we, so maybe you will think that these electrochemical performances that we got are quite low, and you are right. In comparison with commercial lithium-ion, of course, they are quite low. Nonetheless, I just wanted to share with you this here. In comparison with the commercial filaments that I introduced you at the beginning of this part, the commercial filaments that contain 8% of graphene, here you can see represented in the graph by the red line the reversible specific capacity that was obtained thanks to this commercial filament. That was only 15 milliampere hours per gram. So here, even if our performances are quite limited, I agree, they are still much better due to here the huge amounts of active materials that we that we implemented within our homemade filaments. So I just mentioned right now about that was about the negative electrode, but actually we did exactly the same work focused on the positive electrodes. And so I will not enter into details right now because it's exactly the same, but I just wanted to show you the electrochemical performances. And so here again, with the optimized value, optimized composition, we were almost here again reaching the theoretical capacity of lithium iron phosphate in this case, which is about 170 milliampere hours per gram. And so we decided with this composition to produce 1.75 classical filaments and to print some 3D discs. These 3D printed discs, actually, you can see again that you have a huge gap between the films and the values that you obtain for the 3D printed disc. And here again, this is due to the first layer resolution limitation. Then it was needed to take a look by transmission electron to see a little bit the percolation network. And here, unfortunately, actually, I mean, we can clearly see that LFP particles, lithium hydroxide particles, are not really well connected to the percolation network. And so here there is clearly still room for improvement. And in the future, we can imagine to add more conductive charges and also more lithium hydroxide to this particular composition. So now I talked about the negative effort, I talked about the positive one as well. And we tried also to develop a filament for the separator. And so here, starting from a pure PLA filament, we decided and we tried in order to increase a little bit the liquid electrolyte impregnation of the electrolyte. We tried to implement to the filament some silica particles. And so here, by increasing the silica contents, actually, we were seeing that the swelling was decreasing, which makes totally sense because the polymer matrix is the one that is prone to be solvated with the liquid electrolyte. So here you can see that there is a red dot appearing in this graph, and these red dots actually correspond after 10 hours of impregnation within the liquid electrolyte to optimized value. And this optimized value here corresponds to the 7% silica content. So then we produce filaments with this particular composition. And you can see that after 10 hours within the electrolyte, we obtain ionic conductivity value of about 1.2 multiplied by 10 minus 4 Siemens per centimeter, which is quite promising, but still far from a porous polyolefin-based separator, which depicts 10 times higher values. So to summarize a little bit, during this part, we developed 3 different filaments for the negative, for the positive, and also then for the separator. And then, as we developed these 3 filaments, yes, from now on, we can start considering the 3D printing of a complete lithium-ion battery. This is actually the next part. So before trying to print the complete lithium-ion battery, you still need to overcome some printability issues. And so indeed, you know, I mean, in comparison with commercial filaments that are really easy to print, okay, because they are really hard with steel. And here, in this case, you can use classical printing parameters. If you take a look at the composite electrode filaments that we developed, here they are clearly very brittle due to the very high amount of active material in charge. And so it will induce within the piping gear some filament breaks, and also within the nozzle, we will have some clogging. And this clogging and these filament breaks actually will induce then extrusion issues, meaning that right from the start or in the middle of the print, you will have no material that will be coming out of your nozzle. And so this is quite problematic issue. And in order to fix this issue, actually, I mean, we needed to perform some tuning of the printing parameters, such as printing temperature or printing speed as well. And in the future also, you can even imagine to make printer modifications. Regarding the separator filaments that we developed in this thesis, this one was quite flexible. It was not here brittle, but very flexible. And so we got another phenomenon, which is called filament blocking. Here, as you can see, within the driven gears, the filament of tendency to come out the driven gears. And so again, it leads to exactly the same issues, extrusion issues, right from the start or in the middle of the print. You will have no material coming out of your nozzle. And so here again, in order to print, to be able to print this particular filament, you need to make some printing parameters tuning or also implement some modification to the 3D printer. Once and only once you are able to finally print those 3 filaments, both electrodes and the separator, then yes, you can consider to print the whole lithium-ion battery. So here, as you can see, from the optimized filament composition, we developed first a filament, so a 3D printed disc for the positive, This as well for the negative electrode, and one this for the separator. And here, so it's important to mention that the three components were here printed separately. And so here, this is just a battery assembly that we did. So we inserted that into a storage lock. And right from the beginning, when we did electrochemical characterization, we were able to see that we had clearly some liquid electrolyte impregnation issues. Indeed, here, during the first few cycles, you can see that the specific capacity, the reversible specific capacity, was still increasing after 10 cycles, meaning that we have a liquid electrolyte impregnation issue. In order to fix these liquid electrolyte impregnation issues, we tried to implement an infill parameters and also an infill density parameters to the separator. And so here we decided to print the separator with what we call an Archimedean chords pattern. This is actually, these patterns are all automatically generated thanks to the slicer software. And here, as among the open design, so meaning that the liquid electrolyte will be free to move everywhere in the space of the label. Here, and as Archimedean chords is the only pattern among the open design that is able that you can print in only one part, okay, in only one piece. Here, we choose this particular infill pattern. Also, infill density was a huge parameter to take into account, as it is really a compromise between short circuit but also liquid electrolyte impregnation. So then we did exactly the same, but here you can see the only difference is about the separator. The separator, as I said, was printed here with Archimedean chords pattern, and here the infill density was fixed to 70%. And by doing this, and again by doing the assembly of these separately printed components, when we assembled that into a storage block, actually, here we didn't see any liquid electrolyte impregnation issue. So, I mean, so far I just mentioned about the separately printed battery, okay? But as you remember, the main goal of this thesis was to print the whole battery into one single step, okay, in one single print, meaning that electrodes and separator layers need to be printed on top of each other. We are talking about a one-shot lithium-ion battery. And of course, this was, I mean, we did that, but it was thanks to a very huge in-depth technical protocol, as we needed to tune, of course, the printing parameters within the slicer software for each filament. So filament load speed, Newsonian bed temperature, fan speed, flow ratio, and rate ratio. And here today, I would like to introduce you a small video about that. So here it is. So the first step, you need first, thanks to a slicer software, you need to plot all of these printing parameters corresponding to the positive electrode, separator, and also the negative electrode. Once you've done that, then yes, you can start loading here the positive electrode filaments, okay, to the 3D printer. And of course, you need to make the nozzle purging in order to be sure that what is coming out from your nozzle corresponds to your composition, your filament composition. Then you preheat the 3D printer, and you can start doing the calibration. Once it's done, then yes, you can finally print here the first part corresponding to here the positive electrode. Once this layer, the printing is finished, the printer will automatically pause on one corner of the printer, because this is something that we ask the 3D printer to do that within the slicer directly. And then we remove here the positive electrodes, okay, filaments, and the next filament to print is here the separator, right? So here, in a bit, we will see, here we go. Here is the separator filament that we introduce with the 3D printer. Here again, you need to make the nozzle purging in order to be sure that it corresponds to your filament. And here you print the separator directly on top above the previous layer that was corresponding to the positive electrode. Once it's finished, here again, you can see that the printer will stop on one side, one corner of the printer. You will be able to unload your separator filament, and then you start the last step, which corresponds here to the negative electrode filament. So here we go. We add our composite homemade negative electrode filaments. Here again, you don't forget we need to make, of course, the nozzle purging in order to be sure that it corresponds really well to our filament composition. And finally, you can print on top of the previous layer, on top of the separator layer. Here you print what corresponds to your negative electrode. Once the object is actually finished, okay, the printer will stop automatically. And here we go. You have your wall lithium-ion battery. Wall actually maybe not, because here there is still one component that is missing, which corresponds actually to the liquid electrolytes that you still need to incorporate. So if you take a look at by scanning electron microscopy, actually by doing transversal image, you can clearly see here the different layers corresponding to your positive electrode, your separator, and your negative. Here again, of course, the separator here was printed with an infill which was 100%. Okay, and so here again we anticipated a little bit, and we were waiting for having electrolyte soaking issues. And so here, how to fix it? We did exactly the same job than previously. Here we attributed, as you can see in this scheme, we attributed to the separator again an infill pattern. Here this pattern is called Hilbert curves. We printed layer after layer this what you can see in the scheme here, and by checking at it by SEM image. Here you can see in the SEM image that was colored in blue what corresponds to the positive electrodes. You can see in red what corresponds to the negative one, and here in right, if you didn't locate it properly, what corresponds to the separator. In black, actually, you can see that some caves were actually created, and that was this case were created by, this gap, sorry, were created by the separator pattern. And here, unfortunately, as you can see, as you are printing at 100 or 160 or 170 degrees your positive electrode filaments, of course, due to simple gravity, your layer corresponding to the positive electrode will go and fill here the voids that you left thanks to the separator pattern. Here, of course, when the positive touches the negative, it's bad in general, and here you will have, of course, short circuit. In order to avoid these short circuits, we went further actually, and we tried to add just a very thin layer of an extra thin layer of separator. And here, as you can see, so here is an extra layer of separator, and here, as you can see, we have really caves that were created within the pattern. And here we were able to overcome the short circuit issue. Right? And so this was confirmed actually by doing electrochemical characterization. And here, finally, as you can see, we have a proof of concept. Here we were able to print a complete lithium-ion battery, layer after layer, in one single step. So I agree with you. If you take a look at the electrochemical performances, they are still quite limited. And thus, of course, it will be it's needed in the future to make a huge optimization on this electrochemical performance. So far, I just talked about lithium-ion battery that was based on a liquid electrolyte technology. But unfortunately, as I mentioned, we have big liquid electrolyte impregnation issues. And so in the future, even if that was not the original scope of this thesis, okay, we try to went further to anticipate this issue. And so we imagine to develop a solid polymer electrolyte filament in order to move from a liquid electrolyte technology toward a solid state technology. And so regarding the solid state technology, actually here, the main idea was to develop a solid polymer electrolyte filament. So solid polymer electrolyte is composed actually of polymer matrix and lithium salt. That was actually, a huge work was done in the past by Michel Armand on solid polymer electrolytes. And classical materials are normally as polymer matrix polyethylene oxide, PEO, and also LFP side as lithium salt. And here, starting from these really classical solid polymer electrolyte materials, we decided to create a filament. And this filament, of course, that was again a compromise. The filament we wanted to obtain good ionic conductivity. We wanted this filament to be self-standing, and also we wanted this filament to be printable. And so we did an optimization about the PEO LFP side ratio. So we started by doing ionic conductivity optimization, okay, and we just studied this by electrochemical impedance spectroscopy. And of course, it's worth mentioning that here all of these tests were performed actually in, cells were assembled in dry room because LFP is quite hygroscopic, right? And so if you take a look at 90 degrees, which is actually the temperature at which usually we use solid polymer electrolytes in applications, here you can see that the maximum value that we obtained at 90 degrees was corresponding to the sample PEO-LTPSI ratio 20:1. And so it depicted an ionic conductivity here using an interdigitated sample folder of about 4 multiplied by 10⁻⁴ Siemens per centimeter. Here also another thing to mention is that fortunately for us, this particular ratio was self-standing here. But self-standing doesn't mean necessarily that it will be printable. And so we needed to make some check about that. Okay, we need to double check. So here that was quite challenging actually because we needed at the time to move everything within a dry room. So the extruder in order to produce the filaments, but also the 3D printers, okay, to the dry room because the LTPSI is quite hygroscopic. That was quite challenging. And with the filaments that, so PEO-LTPSI 21 that we developed, we tried to print it using a commercial 3D printer. And here, from the beginning, we saw that we have quite issues, okay, that was impossible to print for filaments. And why is that? It's because actually the filament was really soft and also really sticky, okay? And this optical, I mean, what we saw when we tried to print actually was then confirmed by doing in situ cell nanoindentation. So here, all samples were directly transferred to the SEM using a specific transfer folder, okay? So it didn't see the water at all. And here, by doing comparative nanoindentation, we clearly see here that the Young modulus of the filament that we developed, PEO-LTPSI, was quite low in comparison with classical polymer, pure polymer, PLA or PEO. Here, we estimated the Young modulus of our samples to be about 150 megapascal only. So here, the filament was really soft. And again, also from the nanoindentation experiments, we determined that it was quite sticky. Indeed, when you try to withdraw your indenter, it was really sticky to the material, which corresponds exactly to our observation when we try to print. So instead of using a commercial 3D printer, actually, we had no choice but to make some modification to the 3D printer. At least this is the way that we choose. Okay. And so here, in comparison with the commercial 3D printer, the modification that we did was to reduce considerably the length between what we call the driving gears and the nozzle. Here also, you can see that the nozzle of the modified 3D printer, the diameter of the nozzle was enlarged. Thanks to this modified 3D printer, yes, here we were able to print some 3D printed discs, okay, that were tested later by EIS. And so here again, we have one proof of concept, okay, about the printability of a solid polymer electrolyte. Nonetheless, I mean, even with this modified 3D printer, printing was quite complex, okay? So in future, we may have to think about further way to facilitate printing. As conclusion, doing this PhD thesis, so we developed, first of all, a formulation protocol, okay? So as I said at the beginning of this talk, we use slurry solvents as a laboratory scale that was easier to have some samples homogeneous. We had some fins. These fins were used to feed an extruder to have a filament, and this filament was printed into 3D printed discs in order to check the electrochemical performance. We also did many optimizations. The main one is about the plasticizer, okay, within the electrodes. Thanks to this plasticizer, actually, we were able to improve considerably the printability of this filament. But also, thanks to this plasticizer, we were able to improve considerably the amount of active material within the electrolytes, within the electrodes. Also, regarding the separator, we incorporated some SiO2 in order to improve the liquid electrolyte impregnation. And sorry, within the solid polymer electrolyte, we did a PEO-LTPSI ratio optimization in order to improve the electrochemical performances, the ionic conductivity, and also printability. I mean, that was a component. Regarding the printing parameters, we did some tuning, of course, and also, as I show you, we did some 3D printers modification during this phase. So far, during this thesis, we just use a single screw extruder. This is this one actually, and as I already mentioned previously, you needed to have at least 100 grams of materials in order to have a filament that was homogeneous. Here, that was really time-consuming and quite challenging in order to have something really corresponding to your composition. Also, the cleaning was really complicated between two samples of different composition, and here, usually, you cannot add to such an extruder powder or liquid as filling material. So here, every time you needed to add normally the films or at least like pellets. And so here with such an extruder, you cannot avoid the first step, which corresponds to the slurry with the solvent. Okay. In the future, it would be very great actually to move towards another kind of extruder, which is the double screw mini extruder. Here with such an extruder, you can obtain homogeneous filaments with only 15 grams of materials. And also with such an extruder, actually powder and liquid can be used as feeding materials. So here we could imagine to move towards a solvent-free process. Directly you add your powder within this extruder. Okay, you don't need anymore to make some slurries previously. And it paves the way actually. It paves the way towards some polyolefin-based filaments that are actually less prone to dissolve within a liquid extruder. Also, here with such an extruder, the cleaning is much easier between two samples of different composition, as you can directly open the extruder. During this PhD thesis regarding a liquid electrolyte technology, so as I mentioned, we did a proof of concept, okay, but unfortunately, the electrochemical performances were quite limited. And why is that? As I mentioned, it was due mainly to the first layer resolution limitation, and so electrodes balancing for now was not even possible. And so in the future, actually, in order to overcome and to go further, we are trying right now to develop some filament for current collector. So here we are developing a PLA silver copper filament as current collector. And here the idea, in order to overcome this issue, would be to use the current collector filament as first layer. So the first layer, which is subjected to this layer limitation, okay, would be printed thanks to the current collector. And so the electrodes that are above the layer could be down to 50 microns. Also, in order to improve considerably the electrochemical performance of this battery, here we could imagine to make an optimization of the liquid electrolyte if we continue to use PLA-based filaments. We could imagine in the future as well to move towards a polyolefin-based filament rather than PLA. And finally, charge granularity must be optimized in order to find the best compromise between printability and also electrochemical performance. Regarding the old solid-state battery, so as I mentioned previously, we developed in this PhD thesis a filament PO ENSAIT 21, and we were able to print this solid polymer electrolyte filaments, okay, thanks to modifications that we implemented within the 3D printer. And of course, I mean, research direction must go right now to the development of PEO-based electrodes. And also, in order to facilitate the printability, we could imagine in the future to use polymer blends or com-block polymers. And here are two examples actually that use exactly the same materials, the same polymer that we use here in this PhD thesis, which are PLA and PEO. Also, we could even try to go further by doing some very in-depth modification on the 3D printer. Here, we could imagine that we could develop, for example, a 3D printer using directly a powder or pellets as a material source. Regarding the fused deposition modeling, the 3D printing itself, I mean, we did here just a preliminary work, okay? We tried to tune some printing parameters, but of course, in the future, I mean, a really in-depth optimization of these printing parameters must be done for each filaments. And so, of course, the impact of every parameters here must be checked on printability and also on electrochemical performance. Last but not least, I would like to talk and to say a few words about multi-materials printing options, because this is really the future of lithium-ion battery 3D printing, honestly. Right now, what we were printing in this case was just planar, right? We were able to print planar electrode, planar separator, etc. But in the future, as I said at the beginning, the real goal is to be able to print some three-dimensional architectures of the battery. And so little by little on the market, since few years, 2 years actually, we start to see commercially available some multi-materials printing options. And so here in this laboratory, actually, we have one multi-material option, which is here the image on the left, filament selector. And thanks to such multi-printing options here, we are able to print 5 filaments at the same time. So you can one day imagine to print the 5 components of the lithium-ion battery at the same time. On the same layer, you have up to 5 filaments. And so we did some tests actually with these multi-materials options. And here, as you can see, this is the image on the right, we were able to print these commercial filaments, some three-dimensional architectures of the battery. Actually, this is quite small. Maybe I will show in the answer of the joint numbers later. Of course, I mean, the main goal afterwards would be to do exactly the same, but instead of using commercial filaments, to use our homemade composite filaments here. Nonetheless, we are still far from that. Still, I mean, sizer, firmware, and also multi-materials option improvement are needed before reaching that final goal. And finally, I would like to mention also that hybrid printing would be a huge, I mean, a good way also to be able to print in the future the complete lithium-ion battery. So by hybrid printing, I would like to say that it's hybrid printing using different kinds of process. So here we could imagine, for example, to use FDM to print one part of the lithium-ion battery, to use LDM, for example, to print the liquid electrolyte, etc., etc. We could imagine that. So I would like finally to thank my supervisors during these 3 years. They were great help and support. So Sylvie Grosjean and Luc Dupont from the Laboratoire de réactivité chimique des solides, and Stéphane Panier from the Laboratoire de Technologie Innovantes. I would like to acknowledge the FEDER and the Région de France for the funding they provided for the studies. I would like to thank as well all of the collaborators that helped me during this PhD thesis project. I would like also to thank my colleagues from the Laboratoire de réactivité chimique des solides and my colleagues as well from the Laboratoire de Technologie Innovantes, and particularly Monsieur Mathieu Morquet, the Laboratory Director of the LRCS, and also the Mechanical Engineering of Materials Thematic Director, Mohamed Besas. Thank you very much for your attention. I really look forward to discuss with you more in this project. Thank you very much.
Thank you very much, Alexis MAUREL, for this great presentation and this dynamic presentation. So now we can start the session of comments and questions. So we can start with the first week with Mrs. Diana GOLODNITSKY. So if you are ready, the floor is for you.
Okay, good afternoon once again. Do you hear me?
Yes.
Yes, we can.
Okay, so first of all, I would like to emphasize that the project is great and you achieved very interesting results and presented your results very well and logically. And I think that everybody is satisfied with your work, first of all.
Thank you very much.
The second, I have some questions dealing with FDM and with electrolyte. First of all, what is your opinion? Is it possible to decrease the diameter of extruder and printer nozzle in such a way that you can use this FDM technology to print small features? I mean, finally, to get not 60 micron diameter, but to go to few microns.
So in order to thank you for this question. So classical nozzle diameter is about 0.4 millimeters. This is really classical, okay? But of course, I mean, we can diminish. But here the risk actually by diminishing this nozzle diameter is, of course, the nozzle clogging. So meaning that if you have an accumulation of particles or charges, so carbon black or active materials here, for example, you will have some nozzle clogging. So meaning that you will not be able to breathe. So unfortunately, I'm afraid to say that I see very difficult in the future to reduce considerably the nozzle diameter. So that is why actually we try to, I mean, in the future, as you see, we are trying right now to overcome this issue by printing, I mean, the current collector filaments. But the nozzle diameter by itself, of course, we can diminish it, but I mean, in parallel, it will be also necessary to decrease considerably the granulometry of the charges that you are using. Usually, I mean, I think there are some papers on literature that are saying that you need to have your nozzle diameter that must be at least 6 or 10 times the size of the charges that you are actually using.
Okay, thank you. I see. So there is no chance for micro batteries to use the FDM? Your final?
Definitely, I will say that no, you cannot. This is not the main goal. You cannot imagine to do with FDM micro batteries. No.
Okay, I see. Unfortunately. Okay, another question. You told that you used 150 microliters of electrolyte. Did you calculate somehow this volume? Do you know that it penetrates the bulk of the electrodes? Was the electrode flooded, I mean the cell, was the this amount of electrolyte in excess, or it completely was swelled by the electrode and the separator?
So here the electrolyte actually was added in excess voluntarily.
Ah, I see. So the question was long and
so it simplified a lot.
Okay, I see. Okay, so another small question. Do you think that even if you have an excess of liquid electrolyte, PLA somehow can contribute to the conductivity or not? Or
What, sorry?
Do you think that PLA has some contribution to ion transport, or it serves only as an inert matrix?
I see, I see. So actually, and I think this is one of your paper, actually, very recently, you demonstrated, I think, that there are some kinds, actually, of interaction between the lithium ions with the oxygen from the PLA. And so to answer your question simply, yes, the PLA will contribute very, I mean, not like PEO, of course, but it will contribute a tiny part on the ionic conductivity, of course.
Okay, so do you, I see that you agree with me, but why? Can you explain a little bit why do you think that PLA, the contribution of PLA is not so strong as polyethylene oxide?
Why is that? So I don't have a proper explanation about that, but maybe I mean, I think that PLA in comparison with PEO is really really small molecule. I mean, also it's an ether in comparison with PLA, which is an ester. So maybe it has also some influences on that. I know that in PEO, if I'm not mistaken, Michel will correct me later, but if I'm not wrong, we have the formation of some helix 7 units of monomer. In PLA, I have no idea on this. I have no idea.
Okay. Okay, another question dealing with silica. You mentioned also that there is some maxima in swelling and conductivity when you introduce silica to the electrolyte. So why the further increase of silica content is followed by the reduction of the conductivity?
Okay, I'm not sure I got the question because here we didn't hear properly, but I heard that it was about separator and conduction with silica content. So I think I have enough in order to construct a proper answer. So here, by adding more silica to the PLA matrix, actually we were able to to diminish the shrinking. And here it's mainly due because if you have more silica to your composite, it means necessarily that you have also less polymer amounts. And so less polymer amounts, I mean, the polymer is actually prone to solvatation with the liquid electrolyte. And so in definitive, I mean, also the ceramic particles, they are not changing and how can I say, they are not shrinking in comparison with PLA within the liquid electrolyte.
Okay, thank you. And maybe the last question, you showed the measurements of the conductivity in different types of sample holders. I mean, yes. The sample holders which measure the in-plane conductivity and the sandwich holder which measures the conductivity perpendicular, if I can say so.
Yes.
Can you please address this issue? Do you expect the lateral and the orthogonal conductivity differs and why?
So here actually the slides that you were mentioning. So indeed, so what we did here, and that was actually reproducible, we did a lot of experiments to really be sure about that. So here by using different sample holders, okay, by EIS, indeed, we're able to see that the difference in ionic conductivity, I mean, we got some difference for the same sample on the ionic conductivity. Here, as you can see, we got the highest value using lateral, while I mean, with interdigitated comb, we have I mean, values that are really I mean, the trends look the same, but they are decreased, okay, the values. And as you can see, sandwich here is right in the middle. Lateral and interdigitated comb, I agree with you, are both, I mean, in-plane measurements, while sandwich is through-plane measurements. Here, I mean, when we saw these results, we were really surprised, actually, and we really tried to find the good answer. Why do we have this difference in ionic conductivity? And so, first of all, I mean, we were thinking maybe there is a interaction. This is this slide here. We have maybe an interactions between what we deposit and also with the sample holder. Because of course there is something I didn't mention, maybe that was not clear, but all of the 3 samples, I mean, every time the sample of the same composition, that was a slurry that was prepared, okay, within a solvent, and the slurry was directly deposited within the sample holder. So here the preparation method was exactly the same on the 3 cases. So we were thinking also maybe that it could be due to some, I mean, we make sure here that we got no water, we got sure that that was not during the preparation method that we got some issues. And as I said also, we didn't see any interaction with a sample holder. And so far, we don't have a clear explanation here. And so we are doing some tests. So regarding the interdigitated comb holder here, we may think that we have this value because there is an exclusion zone between the polymer and the gold pattern, the positive. And so right now we are doing actually some experiment by changing this the number of teeth on the interdigitated holders. And very soon, hopefully, we will be able to find a proper answer to that.
For sure, thank you. And afterwards, I have one remark. I think that you can found some proper answer in these differences in the original works of Professor Michel Herman. He showed that the ion transport occurs inside the helices and jumps between the helices. And maybe when you conduct your printing, the helices are oriented laterally. And when they are oriented laterally, it is difficult to lithium-ion to jump from the helix to helix, but laterally these jumps are more easier. When you measure the orthogonal conductivity, in the case of printing, because of the orientation of the helices in XY direction, the conductivity in the through plane direction may be somehow impeded. This is my suggestion.
Okay, yeah, thank you very much for this.
Thank you once again. I think that it's enough.
Thank you very much.
Thank you, Mrs. GOLODNITSKY. So now I give the floor to the second reviewer, Mr. Roubaix.
Thank you very much. Hi, Alexis. Can you hear me clearly?
Yes, sure.
Oh, very good. So congratulations. Actually, I really liked this. I really liked your work. Yeah, the work that was done and the way it was organized and presented was very, very clear. So thank you for helping me to understand this.
Thank you very much.
So I have a series of questions, and some of them are questions, and some of them are. I'm curious to know your impression based on what you've done and what you may do in next steps for the FDM. One of them, just in general, is a comparison, let's say, between a 3D printed cell, maybe a planar cell, 3-electrode cell, versus a coin cell configuration. So if we take that as an example, even for multi-material or multi-technique or complex three-dimensional shapes, etc., how do you think you would deal with the difference in compression between the electrodes? Because in a polymer or solid electrolyte with separators that are thermoset plastics, is there a limitation for FDM-based printing of coin cell type batteries that you don't have any compression?
During the compression, honestly, I would say that no. I think whatever configuration would be fine. Also, I mean, here within the electrodes, as you saw, I mean, we have quite a huge amount of polymer. So I don't think that compression would be here an issue, because I mean, in commercial lithium-ion batteries right now, we have very few percent of polymer binder. Here in our homemade filaments, we have up to, I don't know, still 33, it's still so high, right? So about the mechanical aspect, I really think that, of course, I mean, we have also a lot of charges, but I don't think we will have any issue.
And that leads me to the other general query, especially for the FDM. And I liked the approach that you took to tackle the inclusion of the active materials within the PLA, this balance between electronic conductivity, mass loading, and brittleness, mechanical properties. So, what technique or modification would you make if you had infinite time to do this, to solve the issue of electrolyte access to all of the active material, specifically from a gravimetric energy density consideration. In your electrodes with a known diameter for the filaments, what percentage of the active material do you think was accessible by the electrolyte or by lithium ions?
So yeah, that's quite complicated to estimate. Actually, right now so far, I mean, if you take a look at the electrochemical performances that we have done on the curve, maybe I can put it again. You will see that we are just talking about the active material. I mean, we are talking in gram per gram of active material. Let me take it. And I mean, why we started with this is just because we still have a huge work to do in order to be able to consider the whole, I mean, the whole electrode, right? Here it is. Okay, here for the positive. Here, if you consider, for example, what we obtain for the 3D printed disk, you can see that we are really far still from the theoretical capacity value of lithium iron sulfide. And so here, if you consider the total composite, I mean, as you can see, we have only here up to 49% of LFP. So of course, here for the total composites, the performances are divided by 2, right? So we are still far. And here, of course, so it's really complicated to answer your question because I'm not sure we can estimate properly what is the amount of LFP that is accessible really by the liquid electrolyte. But one thing is certain is that by reducing the thickness, of course, it will be much easier. It will be much easier. Also, there is another parameter which is the porosity. We estimated within the 3D printed disk a porosity of about 20%, but actually this parameter must be optimized greatly by tuning the printing parameters. Indeed, if you want to have a much higher porosity, I would rather suggest to slightly decrease your printing temperature and your also extrusion temperature. So maybe we can, in order to have more active material that are, I mean, connected thanks to the liquid electrolytes, okay, available to the liquid electrolyte. Also, there is this kind of parameters. Temperature during the extrusion is really important, I think.
Yeah, I pretty much agree with you. I think the data you show here is probably the lower bound. You've honestly included all the mass of the material, but maybe not all of it is accessible, and the porosity as well. One interesting point from this particular curve, that when you do hit a let's say a C/2 or 85 milliamp per gram specific current, the specific capacity from the positive electrode side drops to nearly 0, but then it completely recovers.
Yeah.
And so looking at examples of this, even for non-3D printed materials, there's been quite a few reports of really an out-of-plane electronic conductivity limitation. And that's one question I wanted to touch on. When you have, in what situation and what polymer blends or what additive was the best for maximizing the electronic conductivity in a filament, and how did it vary with the number of layers in a print? Was it very sensitive to the number of layers or more sensitive to the composition?
Yeah, I see. So here, I mean, as I said, we just employed carbon black and carbon nanofiber. I mean, in this work here, we didn't actually study the impact layer by layer. So I cannot unfortunately answer your questions. But okay, what I can say is that I really think that if you consider this, in that case, yes, carbon nanofiber might be a better way in order to have a proper electronic conductivity. I mean, carbon black are really great here. I mean, we did our optimization with carbon black, but I mean, they are really too tiny. So maybe in order to have a good electronically, I mean, a good percolation network of these particles between the different layers, I would rather suggest, yes, to use a carbon nanofiber or carbon nanotube.
And then you mentioned the, this is more of a curiosity question, because I realize that you've investigated quite a lot of the parameters for tuning the 3D printer. But before I ask the question, I want to say that I think that's one thing that struck me in your work. Instead of trying to change technique, when the FDM had some limitations, you decided to fix FDM, or at least try. That was a nice thing to have done. But when it comes to NP or electrode balancing, this may be difficult depending on the polymer blend mixtures for anodes and cathode formulations, for example. But do you think it would be possible to go down the anode-free route, or to heavily lithiate one side of the cell to have less dependence on the formulation for the other side, for example?
I'm not sure. Can you repeat the last part of the question? Would it
yeah. If mass balancing can be an issue, do you think that optimizing the anode and cathode formulations separately to work together is best, or can you heavily lithiate the cathode side, for example, to go down something similar to an anode-free type cell, in which case you worry about just one electrode by FDM instead of two?
So I would say that this electrode balancing is really, of course, complicated, as you said, to implement in the future. And in order to do so, I really think that first we should just focus on independent electrodes, mostly at the beginning. And also, and this is a little bit what we tried with Stéphane Panier, one of my supervisors here. We tried, as I mentioned at the beginning of the series, to make some modeling study. And I really think that by using modeling as a tool here, we could maybe be able to determine maybe not the exact composition to use, but in order to determine a little bit, and I think it would considerably help us in order to find the proper balancing.
Yeah. And I guess the last two questions are again looking towards the future, for example. So when it comes to organic electrolytes, and they, well, in some cases they're useful because they can degrade the plastic and reveal the active material, and you see capacity going up instead of down. But what techniques would you choose, or what materials, if you were to change the technique from FDM to another one, in order to use organic electrolytes to have a higher voltage system, for example?
Sure. So I don't know if these organic materials are thermoplastic, so I'm not sure. So that's why also you need to think about if there are thermoplastic cases, you can use FDM. If not, you need to move towards another kind of techniques. Then, I mean, organic small polymers, they are really nice. This is really a huge perspective on that. Unfortunately, so far, I mean, conductive organic polymers, I mean, it's possible to obtain this, but very tiny or small amounts. Here, as I said previously, I mean, we need 100 grams of material in order to have homogeneous filaments, so it's quite complicated. So that's why, as you said, FDM might not be the good technique. So maybe here we could imagine, and the easiest way to do that would be thanks to liquid deposition modeling by using inks. I really think this is the easiest way to do so, because also thanks to liquid deposition modeling, this is also the other techniques with FDM that you can perform as well multi-material printing. Okay, and so here maybe you can imagine as well one day to be able to print the whole battery or combining techniques, but yeah, so maybe organic based I mean, components of a lithium-ion battery could be done with liquid deposition modeling.
Yeah, that's true. It's the organic electrolytes at least can be difficult to work with some of the plastics. So the last of the questions for now is really really the devil's advocate question. If you think about applications of these cells, so
Yeah.
I assume you can do multi-material methods and you have solved some of the technical issues. There are lots of them for this type of approach. But do 3D printed cells really need to be rechargeable? For example, if they were recyclable plastics, very lightweight compared to aluminum or other metals used to make coin cells, do you think there would be a direction where they're just single use?
This is a good question. Here, why are we using 3D printing? It's mostly because I mean, you can make free shapes, right? You can make free forms. Here about application, so we are still far from doing a three-dimensional architectures of the lithium battery, right? So we are just talking right now, and we are also talking about just a battery that will become the object. So so far with the performances that we have, of course, it resembles much more to a primary battery than to a secondary rechargeable battery. I totally agree with that. In the future, if we are able to, of course, obtain, I mean, increase, enhance a lot of these performances, then yes, we will be able maybe to, I mean, to look for their implementation in some applications where yes, you need to make it rechargeable. But so far, yes, I agree. I mean, there is still, I mean, a lot. I mean, there is still room for improvements on the electrochemical side. Definitely, we are still very far from having this in real applications. Yeah.
Okay, I have, I guess, a lot of other ones, but I know you've addressed them in the thesis document itself quite a lot. So there's what's not in the presentation, there's a lot of work in the thesis, a lot of testing of the materials, especially the mechanical properties of these materials, which I found very interesting. One little question, and it's not so much of a test, but I'm curious, in the mechanical property testing for these, were they always based on the new filaments, the composite filaments that you made, or did you ever test some of the mechanical properties of the final printed cell, for example?
Yeah, so basically what we have done right now, I think on the thesis, was just on the films. Nonetheless, in order to, I mean, that wasn't the film, but the films, we did injection molding, okay, with these films. And so we did injection molding in order to simulate, the extrusion of our filaments, actually.
Right.
So we did injection molding, for example, I remember, but maybe for the negative electrode that was at about 170 degrees. And that was actually at that time, that was exactly the same temperature that we were using in order to extrude our filaments. So that was a way in order to try to simulate a little bit this extrusion. But of course, I mean, when you are doing tensile strength, I mean, in order to check the mechanical performance, of course, I mean, you need to have this, I mean, samples with a particular shape, right? And so, of course, unfortunately, you are not able directly to put, I mean, you cannot put directly your filaments 1.75 diameters and do tensile strength like this, because it doesn't follow any rules, okay? Then, regarding your questions, yes, we did print some how do you call it, seven dumbbell shapes, I think, in order to make the mechanical strength test. And so we printed this, but I think we only printed this in the thesis when we printed with PP instead of PLA. So here, I think the last chapter of the thesis, chapter 5, when we are doing mechanical testing, yes, here it's on the I mean, after printing by FDM and also after printing by SLS. Of course, I anticipate your next question. Of course, if you test after injection molding and if you test the mechanical performances after printing, obviously, what I expect is that the mechanical performances will be somehow different, because I mean, depending on side, on which side you print, okay, maybe you will have, you know, in FDM you print layer by layer, and so somehow maybe if I mean, there is a small space, or I don't know, between two layers, somehow it will maybe have a bad impact on the further mechanical strength.
Yeah, that's what I was thinking of. Sometimes the crisscross shape of the printing can be different every time you print.
Yeah. If you print on one, if you print on, I mean, depending on the way you print, of course, I mean, it's anisotropic, I think we call it like this. And depending on the way you print, maybe also your particles, if you consider, for example, carbon nanofibers, I will be aligned in one side, in one particular side, and if you are in the same side that, you know, you do your mechanical testings, it may affect also the mechanical performances, that's for sure.
Okay, yeah, thank you very much. One last one, more about you. This thesis had two interesting personalities in there. One was on the 3D printing aspect itself and all of this, and the other one was on the materials and the electrochemistry side. I'm curious, which one did you personally find more interesting / challenging out of the two sides?
Yeah. So actually, I'm coming more from the electrochemistry background.
Okay.
My master was about energy storage and materials. So I had, I mean, I didn't know anything about 3D printing before coming here in Amiens. Actually, the last semester, to tell you the truth, the last semester of my master thesis, I spent it here in Amiens working on the exact same topic with Sylvie, Loïc, and Stéphane as supervisor as well. So I already started 6 months with them before the PhD. So I didn't know before that, I didn't know anything about 3D printing, but really, I fall really in love with this technique. I think it's a really beautiful technique that allow you plenty of possibilities. And so to answer your question, I don't prefer any, I mean, I don't prefer one or the other. And that's actually why I did my best in the future to find a new professional, I mean, a professional career, but combining both, so batteries on one side, but also 3D printing. And I'm really happy to tell you that I will continue working in this particular project, not here in Amiens, but I will work on both techniques, printing and batteries.
Oh, good. Okay. Well, thank you for this. It was a very interesting piece of work.
Thank you very much.
Or Dwyer, I don't know how we want to say it. Okay, thank you. And Alexis for the discussion. So now we can continue with the examiners. So we can start with Mr. McDonald.
Okay, can you guys hear me?
Sure, yes.
Okay, all right. Well, first off, fascinating presentation, of course. I learned a lot about electrochemistry, so that's good. And I'm probably not going to ask any probing questions about the chemistry because I'm a mechanical engineering professor, but I've got some ideas about maybe the future directions. And you mentioned that stereolithography could not provide multi-material.
Wait.
And that's true technically from a commercial standpoint. But I published a paper in 2009 on multi-material microstereolithography. And I'm just curious, we can get like 3 micron resolution, and we at least demonstrated 2 materials. But what can you say about how you might be able to combine this with photopolymerization? What would be your comments on that? Because it may be a really intriguing future direction, I think, that could provide very, very, high resolution, complex geometries, but maybe with a limited build volume of say 2 centimeters on a side.
So I totally agree with you. So yes, I mean, you published this paper about multi-printing by SLA. Also, Christopher Hansen, I think, is working on that actually, on multi-printing from University Mass Lowell, is working as well on SLA multi-material printing right now. So when I said that during my presentation, actually, what I wanted to emphasize is that it's not widely commercially available on the market. You don't find this kind of multi-printing option via SLA. So of course, in the future, I mean, this is great perspective because, as you said, I mean, we can print very tiny devices. So regarding the size of the bed, you know, of the bat, I mean, it's not an issue because talking about batteries, I mean, generally we think very, very small. So it's not an issue. The smaller, the better for us. And so, of course, I mean, the tricky part then is to find the good materials. So about electrochemical materials, I mean, that would be fine. But then regarding some polymer matrix that can be printed via SLA, I think you need to think also to find the good UV curator for this kind of polymers. The polymers must be inert with the liquid electrolyte if you are focused on a liquid electrolyte based technology. So there are tiny parameters that need to still be, I mean, really well think. I think I mean, you need to think a lot about this tiny fixing these tiny problems at the beginning. But yeah, definitely with this kind of technique. And hopefully one day it becomes really widely commercially available. Of course, you can really imagine to move towards the 3D printing of a complete lithium-ion battery in the 3D-dimensional architectures as I was showing you at the beginning of this. Yeah.
Awesome. And then maybe just one other possible approach that you could take with additive manufacturing would be, you know, an ink jetting approach, material jetting. It seems like that may be more limited in terms of the three-dimensionality of it. It's really 2.5D. But I really think this stereolithography could be an interesting approach. I just don't understand the chemistry sufficiently. But I know that, yeah, it's definitely possible to have very intricate, you know, interwoven, interdigitated, three-dimensional structures that have multi-material. It's definitely there. The system we did in 2009 had many manual steps, but those could be automated, and it just seems like a very interesting approach, possibly that would at least, you know, deal with the challenges that you have with FDM and resolution. But in any case, great. That was a great presentation. I enjoyed it for sure.
And one word about the injects that you were mentioning. Actually, in the past, it's worth mentioning that a lot of work has been reported on printing via inkjet techniques, but mainly, and that's why I didn't consider it here in this PhD thesis in the manuscript. I mentioned right from the beginning that I mean, with inkjet printing techniques, unfortunately, the main issue here is that you cannot generally obtain a battery that will become your object. As you said, we are quite limited to print a very, I mean, complete, I mean, an object three-dimensionally speaking, right? It's more planar. So that's why I didn't consider it here. But as you said, I mean, also macro inject printing technique could be a good way to maybe to investigate it.
Okay, and then just one last comment, and I just, this is kind of science fiction or maybe blue sky research, but last week I was invited to collaborate with a company called Made in Space, and they have an FDM printer currently in the International Space Station, and they're about to do stereolithography, and I don't know how they're going to do it because it's a liquid-based approach, so it dodoesn't make sense to me yet, but they're doing ceramics. And one of the advantages is that the suspension of the ceramic particles in the photocurable resin has better homogeneity. And yeah, do you have any comments on like space-enabled manufacturing? I say that for entertainment purposes mainly, but what do you think?
Actually, you already mentioned that during your last week talk, I think that you said, so I listened to you about this opportunity to print ceramics in space. And yeah, I mean, as you said, so if I'm not mistaken, they were printing via SLA some ceramics, and after, of course, I mean, that was needed to make thermal annealing, if I'm not mistaken, right? And so I don't know if you listened to, I mean, if you heard me, I was saying, so they were able to print ceramics by SLA, but of course, after you need to remove the polymer and, I mean, so to do thermal annealing. So here, such components, I mean, we could print, for example, with ceramic, as I said, for example, the separator. Here you see that the separator will introduce silica on it. So maybe if we are able to print in space, I don't know, a separator containing silica, that could be improving maybe somehow the performances of the ionic conductivity. I don't know, but yes, this is really interesting that you're able to work in such a project. I really think that, of course, I mean, here the particles, as you said, in space, they will go onto I mean, there is no gravity, so of course, I mean, a lot of parameters can change, and of course, it could be a good opportunity to check the performances that may affect. Yeah.
Well, it's a fascinating idea of somehow leveraging microgravity in the vacuum of space, and I just it's really intriguing to me. But yeah, anyway, it was a great presentation, outstanding.
Thank you very much. So now we can hear Mr. Armand.
Okay. Thank you, Mrs. President. I want first to thank the thesis advisors who have invited me. I have to say that when Loïc and Sylvie mentioned about 4 years ago the concept of 3D printing of batteries, I thought it was an elegant curiosity, and I'm quite convinced now. I think it's not only a curiosity, but a possibility. And Alexis, I want to congratulate you, not only for a beautiful presentation, but for a beautiful manuscript, which I had a real pleasure to read.
Thank you very much.
Yes.
Thank you very much.
I've been aware, I've been discussing a few times, and especially for Sylvie and Loïc, the new findings of your thesis. And I believe that what you had in your presentation, the printing of the LRCS battery on video, was something which is the apex of your presentation.
I would have loved to show you that in direct here in the laboratory, but unfortunately, I mean, due to COVID situation, that was not possible. But I really look forward to welcome you here in America here, and to show you that directly, this printing and what I did in the video. That was, I mean, that was in order to show the jury members, I mean, what was done on the laboratory, right? And I would have loved to show you that, because it just takes 2 minutes to show you this, but unfortunately that was not possible due to this pandemic, and that's it. That's like unfortunate.
And of course, I will have some questions. And I think the most fascinating thing you can think of 3D printing is gyroidal structures. Yes. And, imagining a battery which is gyroidal, except in my poor 3D representation of space. I can imagine what you have shown, a gyroid with 3 layers. But I mean, when you want to have a battery, you want to have a bulk, a piece of a battery, and you want to have 2 wires, which is a positive and a negative. So how are you going to collect the current? Are you going to make a 5-layer gyroid? Is it possible? And what shape will it have, and so on?
So thank you for your question. So theoretically, yes, thanks to 3D printing, multi-materials option, yes, it would be possible. But the question is, what scale, all right? if you are talking about something very, very small, unfortunately, no, it's clearly not possible. Also, gyroid architectures here is not maybe not the most easiest one to print here. And so in the manuscript, I think I mentioned that maybe here's a good approximation between the electrochemical and aspect and the printability of it. I suggest that maybe the cube here could be the easiest one maybe to print without having a short circuit.
I don't have problem with the cube in terms of the current collection and so on.
Right. And so to continue on this cube, actually, so we try to make to print it here. I show you an example. Here, actually, I have it in my hands. Maybe you can see it with my camera. It's it's quite small, but maybe not small enough in order to have it in a proper battery, right? I mean, battery, we would love it to have it maybe a tenth of this size. But here, about your question about where are we going to put the current collectors?
The leads.
So, I mean, on the gyroid, we didn't think about that, honestly. But here, for example, for the cube structure, here, as you can see, I mean, we could imagine to implement first filaments and to print the packaging, okay? And within this packaging, we would have the filaments printed with the positive electrodes, the negative electrodes, the separator or solid polynitride, and also a part in order to collect as current collector. Yeah.
Okay, thank you. I'm clear, as I said, for the cube, but the multiple gyroid is a curiosity.
Yeah, and multiple gyroid. So here, in order to have current collector, as I said, you would have to implement. I mean, the easiest way to do that would be to implement current collector parts within the gyroid itself. So you will have a gyroid not with 3 materials, but with 5, which is quite complicated to print afterwards, I think.
Okay. Of course, I will have more questions, but I mean, taken from your document, your presentation was impeccable, as I say. I mean, there is a question, the jury is still out to know whether the plasticizer PGDME is volatile or not. I mean, in some you make the hypothesis that it stays, you make the hypothesis that it evaporates. What is your feeling about the situation?
So there is still a lot of improvements that must be done on the plasticizer. It was really not easy in this PhD thesis to determine and to estimate what amount of plasticizer had evaporated. Also, there is a huge optimization on the storage of our samples, because I really think if you store it, I mean, in dry room, or if you store it in a glove box, if you store it here in this amphitheater, I mean, the storage condition will affect, of course, this plasticizer evaporation. And so here we didn't, I mean, we were not able to determine clearly what amount of plasticizer was evaporated. Surely, I mean, there is a huge part of it that is evaporated. We are sure of that after extrusion, but after printing. And actually, I mean, I did, for example, I created a filament, okay, for example, for the positive electrode. And after so my filament, I was able to print with it. So it was really flexible, really easy to print. And after 1 year, I checked my filament yesterday morning, and my filament is really, really brittle. Maybe I can show Professor CAMPAGNE here later. But the filament is really like a raw spaghetti. Really, I mean, worse than this. You can really break it easily. So, of course, the plasticizer is going to evaporate. We are sure about that. When? This is the big questions. And also, it depends, I think, I mean, the filament is going to also evaluate with time, but also with humidity parameters, temperature parameters, and this is really a huge work that must be done on that.
Yes, I mean, your answer brings me to the what was my next question. I mean, how good PGDME, how good a plasticizer is it? You say after 1 year, your compound became like a spaghetti. It could be evaporation, but it could be slowly demixing of the plasticizer and the PLA. So the question is whether the PGDME is really compatible except in the melt with PLA.
Sure, this is a good big question, and actually, I mean, future work may involve as well the study of other kinds of plasticizer. Here in this thesis, we just study four different kinds of plasticizer, but in future we could imagine to try many kind of plasticizer and to find the best one. PGDME 500 works fine for this thesis, but maybe we would find better. I totally agree with that. Yes.
But you were very lucky. I read with consideration that you were able to intercalate lithium into graphite in the presence of PGDME.
Yes, yeah, that was a good issue as well, because I mean, if I'm not wrong, also you have exfoliation with propylene carbonate, for example.
With shorter PGDMEs, if you have got 5 oxygen, it intercalates. You have 10 here, and it does not intercalate. So you are really lucky. It was
Yes, and I really think also this is something that I mean, people working on FDM of lithium-ion battery must consider is really to use and implement plasticizer such as PGDME 500 or other kind of plasticizer in their next and future studies, because so far on literature, people create some polymer-based filaments, and somehow they are quite limited. I mean, the loading of active material and loading of charge is really limited, and this is mainly due because people don't necessarily try to implement a plasticizer. So I really think that plasticizer generalization is the future of lithium-ion battery solid printing via FDM. Yeah,
I totally agree. No, thank you. I will shift now to the current collectors. I mean, you did cleverly took some copper particles, copper beads, which are very nice beads, but are not conductive. So you coated them with silver.
Yes.
Except you have an electrochemical impossibility. If you're going, absolutely, I mean, you have cementation of your copper, of your silver on the copper, except electrochemically, if you're going to use something with silver, silver will alloy with lithium at the potential of the graphite electrode. So do you have a substitute for that?
Oh, no, not for now. And actually, this is why, for now, I mean, we just consider it for its use as, I mean, as a negative electrode. I will say that this is just an ongoing experiment so far that was done by a master student that I had under my supervision with me. And so here, I mean, that was just some twice where we didn't check really well. We didn't even make a 3D printed disc yet in order to check and to perform electrochemical characterization on that. So, I mean, very soon we will do electrochemical characterization. But yeah, maybe, I mean, silver copper may not be the best way. There is something interesting I would like to mention. I think this is Professor Eric McDonald that in UTEP they are implementing current. I mean, I'm thinking about another idea. Is that, for example, in UTEP, I think they use they are able to print directly and to deposit a wire. Okay, so while printing, you deposit a copper wire, for example. And here, I would love to imagine in the future that instead of having to develop current collector filament here, directly we somehow will be able to deposit this wire corresponding to the current collector. And that would be even better because metal wire of copper, of course, would depict a much higher electronic conductivity.
Thank you. That's a very
So
good
current
answer.
collector filament is very experimental for now, and I mean we are developing this in order to to overcome the first layer resolution limitation that we got with FDM. But on future, I think we can do much better than this, and I think by printing these kinds of wire, I think it would be much better in order to use it for use as a current example.
Okay, I have plenty more questions, but I don't think I will take more of your time. I want to congratulate again you, I mean, for the manuscript, as I say again, and for the presentation, which was very clear. You did not address, you skipped the problem of laser fusion, sintering, and had many questions on that because of you get completely different structures and so on. But we can hopefully discuss it later when you are still at Amiens, and I will come there.
Yes, under other circumstances than COVID, hopefully.
Okay. And Mrs. President, thank you very much.
Thank you, Mr. Armand, for the questions. So now I give the floor to the last examiners for Mrs. Jules.
We don't hear.
You need to speak louder, Sylvie, please. Since you remember, they don't hear you.
Okay.
Perfect.
So I thank you, Loïc and Stéphane, for giving me the opportunity to be part of your group. Alexis, and along with the expert in the field of 3D printing and batteries. So I will talk about you, Alexis. Alexis, you are a master master's student, and you came in for your internship, and you tackled this new topic with enthusiasm. And in close collaboration with Stéphane and Jules. So it was a new topic, a new collaboration for all of us, and it's quite challenging.
That was.
As you are very curious, open-minded, hardworking, and love sharing and communicate, you brought this topic to life and made it progress fast. Even, as you said, there's still room for a lot of improvements. Always proactive, be autonomous research by yourself for technical and scientific help from Benoît, from Mathieu, Karine, Aurélie, ENSAIT, Arash, Pachata, from Président, and also receive precious advices from Michel, us. You didn't hesitate to develop fruitful collaboration with international labs as with Finnish researchers. We got a Fulbright grant. We hope that you can go overseas in February or Islam.
I hope so.
Who were also actively involved in the life of the laboratory. You took the heavy responsibility of the blood box with Anna carrying urban bottles, training a lot of students, etc. After Benoît's dispatcher, you did the temporary hospitality of the Imperial School.
I tried.
And training students as well, and welding wires, welding corners in the lab, and propose the first draft of the book. Help shoot and use the screen printer of the lab, and use the courses with students of the university. So you did all this activity with great contribution. So thank you.
Thank you, Cindy.
What I can complain about is I don't have the recipe of all the cakes you cooked for student room on Friday afternoon.
You love those cakes.
So seriously, I really enjoyed sharing with you on this topic, and I wish you all the best with successful academic or real career.
Thank you very much, Steve. So for jury members who don't see, actually, we have only one microphone for jury members. So between each talk of the jury members here in the amphitheater, actually, we need to clean the microphone. So this is technical part here. So
Okay, so
it's clean.
So now it's my turn. So I would like at first to thank Alexis and your co-supervisor for the invitation. It is really a pleasure to be present here for this very interesting research activity and innovative also. I would like to congratulate you for the quality of your manuscript and also for the quality of your presentation. It was very clear.
Thank you very much.
You tried to highlight the results, so it's a good point. So you understood the majority of my questions, but I have still
Some
2 or 3 questions.
sure.
Yes, I would like. Okay, so for the preparation of your nanocomposite, I call this nanocomposite. I don't know the name you used.
Or composite. It's
Composite,
fine.
but I prefer nano because you introduced nano.
Oh, sure. Okay. Fine.
Matrix, so nanocomposite. You decide to increase the dispersion, but could you define what is a good dispersion? Because I think that it's a compromise. It depends on the targeted property. I agree with you. If you want to increase the mechanical property, you have to avoid agglomeration of charges. But if you target electrical conductivity, it's a compromise, as you said, between a good dispersion and not so good dispersion, because you have to promote the creation of the fast calculation. What is your opinion?
Yeah, so here, I mean, first of all, about solvents. Solvents are bad, okay? And so that's why, I mean, of course, in future, we want to, as soon as we can, I mean, we want to remove the solvents. Okay? That was the slide that I showed just previously. So here, this one. Here, the extruder that we use, as I said, we couldn't directly, this was actually the extruder that we got here in the laboratory. And unfortunately, with this extruder on the left, we were not able to add a powder. So we did it on the 5th chapter. I totally agree. We tried to do that. But that was, I mean, that was very complicated because we had leakage of powder. So that was, I mean, that was not here a good idea to do that, but still we did it in order to remove also the solvent. Regarding you were saying about the homogeneity within the filament. So you say from a mechanical point of view, we don't want agglomeration. To me, I will say that from an electrochemical point of view, it's the same. Why is that? It's because if you have all of your active material, for example, that are agglomerated in one part of your filament, then if they are totally englobed within the whole polymer matrix, then you will have 0 electrochemical performances. So you see from the electrochemical point of view, actually, this is exactly the same than the mechanical one. You need to have sample which is homogeneous. And so as, I mean, with this extruder, we couldn't print directly powder, and and that was the main issue here. Also, even if we could have put powder, here this extruder is single screw, meaning that it doesn't really mix properly. So even if we were able to implement and to feed this extruder with powder on it, we will not have a homogeneous filament. Usually, when I did that for the 5th chapter, the first filament that I received, okay, that I hold, was not homogeneous. And so what I had to do was to cut these filaments into tiny pieces, so repelletized it. So, but here we don't have a pelletizer. I think, I mean, that was quite long because I had to cut with my scissors to do that. But then we needed to feed it again and again, and so at least 2 or 3 times in order to have homogeneous. Yeah, and so this is why it's really important in the future to move towards a double screw extruder like this. This is super important. I would say it's even more important than to have a good 3D printer finally, because here this project is, yes, it's about 3D printing, but it's also and more about composite filament formulation. And so here, to have a good extruder that allows you to test different composition with very few materials and also to have something homogeneous is the key to this process, is the key of this thesis.
And you didn't problem with the viscosity, the problem with the extrusion, because the quantity of your materials is very high. So maybe you can play with polymer with lower molecular weight, maybe, I don't know.
So we didn't try to change the molecular weight, but to tell you the truth, yes, we've got some issues by doing extrusion, also by doing printing. As I said, first of all, about printing, we had very often, we had sometimes clogging of the nozzle, okay? And about the extruder itself, yes, we were able, of course, to block as well the extruder. That was quite complicated and challenging to dismantle it, because this one here on the left, this extruder is not done. Normally, you cannot dismantle it. Or, I mean, you can, but it's quite complicated. And so with the electrodes, we didn't have any issues. But lately, that was 3 weeks ago, we got an issue for the current collector. Because for the current collector here, we implemented and we added directly metals particles. You see? Yes. And so, yeah, yes, of course. But also, at the end, so when we tried to dismantle the extruder, because nothing was coming out, when we tried to dismantle with Stefan, we did that. That was quite complicated because actually we got something very, very solid and very hard at the very end of the nozzle of this extruder. And that was just the metal that was compacted at the very end of this nozzle. You see? So,
yeah, it's a good idea, because I think you increase the thermal conductivity of your material.
Sure. Yeah.
Okay. So I have also a question on this choice of PLA.
Yeah.
Because you mentioned that 6 months after, I don't remember what you said, but you are Spécialité.
So that was about the plasticizer.
I don't know.
Oh, okay. So I will. Okay, I will explain again.
Problems,
yeah.
Of course, because the problem of plasticizer is solution, but PLA is very sensitive also to humidity.
Sure.
And to hydrolysis reaction. So I think that your choice to work with PP maybe is better, because did you study the aging of your materials?
The what?
Aging.
Oh, I see. Yeah. So no, we didn't. Okay, with PLA, but this is a work that must be done. And actually, we did a small experiment here in the laboratory. And just simply, you take, you print pure PLA, okay, from the pellets without any plasticizer, just pure PLA. You put that in liquid electrolyte. Depending on the liquid electrolyte that you will choose, it will dissolve instantly, or it will dissolve in a year. You see. So we did that at the beginning of this project. We started using EC DMC electrolyte, which is quite very classical. And here, instantly, we saw that it was dissolving within the electrode.
What is the
Instantly.
pH of your electrolyte solution?
I don't know.
Because the hydrolysis reaction.
Sure, maybe it may affect. Yeah. Yeah. And so I cannot answer you unfortunately about the pH, but then we move towards another kind of liquid electrolyte. This is the one that was used here in the thesis, which is called DEC. And here with this one, at least at the short term, we didn't have any issue about that. So this is why we chose this. Nonetheless, in the long term, if you take so a disk of pure PLA, you immerse it within this electrolyte, so that's one I mentioned here. After a year, you may see that it may be degraded. Yes. It may be degraded. And so again, I mean, this is super interesting, and there is actually a huge study that must be done on that in order to determine what is the impact, the final impact of liquid electrolyte that we use with PLA. And there is a study about that, from Reyes et al. And they did, I think I mentioned it in the business, I'm sure I mentioned it. They developed a PCEMC, I don't remember exactly. I mean, they did an optimization of the liquid electrolyte for PLA. And they suggest other authors to do the same and in the future to use this particular electrolyte. We didn't check if we got exactly the same performance. We didn't check anything. But that could be a good way, yeah.
Thank you. If I have well understood, the electrochemical performance is linked, in relation with the level of electrical conductivity.
Yes, of course.
Do you have an idea of the targeted level of electrical conductivity?
So I will say that it's a compromise. If you don't have enough, okay, let's talk about the negative electrode, for example. If you talk about the negative electrode here, your active material is graphite. Graphite, it's fortunately for us, I mean, graphite is already conductive. So here you see it's easy. It's quite easy. Nonetheless, if you take on the other end the positive electrode, here the active material is lithium iron phosphate, and lithium iron phosphate, if it's not coated, it's insulator. So first of all, here the lithium iron phosphate that we use was coated, okay, in order to improve the conductivity. And after, of course, I mean you need to implement some charges, some conductive additives in order to improve your electrical performances. And of course, these electrical performances are linked with final electrochemical devices. Nonetheless, an important point, it was reported in literature that if you put too much amount of conductive additive, let's say carbon black, for example, electrochemically speaking, it will be bad. Okay, so there is just a compromise for each. Yeah, I think you will. If your content of conductive additive is really too high, then you will have a high irreversible specific capacity during the first cycle.
I have a remark concerning the introduction of pesticides. I agree with Mr. I don't remember pesticides is harmful for humans. So maybe you can think to another way, is the introduction of elastomer to make a mixture between elastomer and PLA. We have already worked on this part at the laboratory, and it increases the softness of the material.
So that would be indeed a good thing to implement. Elastomer, you're talking maybe, I think, about TPU.
Yes,
no? TPU, because of course you need to make sure that it's thermoplastic.
Of course.
Right? So you cannot choose any elastomer. You need to choose. So here TPU. I agree.
TPU, or you have also
yeah, maybe. Okay. And here you need to make sure, and this is why it's complex. You need to make sure that, as we were saying for PLA, we were saying about PLA reacting with liquid electrolyte, you need to see also the same thing, you know, for TPU or whatever elastomer you want to choose. The impact of water, the impact of the liquid electrolytes, the impact, you know, how it is going to react. Exactly the same study needs to be done. So far in this thesis, we just focus on PLA. But of course, I mean, first of all, we need to answer these good questions on PLA. And why not in the future to implement another and to make it blends? Yeah.
Okay, and last question, because did you study the influence of the parameters of the process, like the temperature of the platform, how you deposit each layer, the direction of layers, the pressure between the nozzle and the
This is
the different
I
layers?
know.
Because I think you have proven of adhesion between each those three layers.
This is something I would love to do, really, and I will maybe not have time. But this is here actually on bottom left, research direction. So here I just mentioned some printing parameters, but actually these printing parameters will affect the layer adhesion, many parameters. And so I really think that it would be a very nice study to do to make an in-depth optimization of all of these printing parameters, because just by changing the printing temperature, you change the printing temperature, the porosity will change, the electrochemical performances will change. Also the mechanical, I mean, the viscosity within the nozzle will change. So it will affect the mechanical properties, but also electrochemical. I mean, there is plenty of parameters that we need to optimize, of course. And it's quite complex, but very interesting. Yeah.
Yes. Okay, thank you very much.
Thank you very much.
For your answer. So now I give the floor to your Professor and the first one. Yes.
So we watch the microphone again.
Thank you. Firstly, I would like to thank the member of the jury to begin for the defense of Alexis. Thank you for your question. I know some of them because they are very interesting. I think for our future works about carbon nanofibers, I think we have to do it because we can increase the conductivity, but also decrease the viscosity of the polymer or the field. So I think it's a good way to try to increase the amount of active materials in the polymer. I would like also to thank Sylvie and Loïc to propose to me to work on this topic. If I remember, the first meeting was in 2014, and the kickoff of this project was in 2017. It's what we call the French activity. And so at the beginning of the project, I had the feeling that this topic is very far off my research ones. And how to say that? And but with the help of Sylvie about the electrochemical and with the help of Alexis, months after months, I begin to understand what happened in the battery. So, to be honest with you, till now, I think all the chemistry part, a lot of problems to understand this part. But today I'm very, very happy to do this collaboration, and I'm very excited to continue this work with you, because this topic is in tune with science. Just look at your perspective, given also by Alexis and this presentation. So we know that we can work on this topic maybe during 10 years, because from additive material point of view, I have a lot of ideas, and I still know that. So, so it's a very, very good thesis. And so, and for me, very good collaboration between people who don't have the same knowledge. And I think this is a very good example today to make this kind of collaboration. So if I resume, we have a very good topic. We have a good supervision team, or not so bad. So now the last ingredient to have a very good thesis is a PhD student. And what is a good PhD student? So for me, of course, he has to have a very good scientific background, a desire to understand, to learn, the capacity to overcome the issue, and the capacity to make some proposition. And we have a lot of work because we found it is Alexis who had all this skill. And for example, he explained to you when you arrive in Amiens, he has no background in mechanical engineering. So what he did, he bought a 3D printer to build himself, not without difficulty. And I think it was the best way to understand how it works. And after that, I think today, if you ask him to mount a 3D printer, he can do it with his eyes closed, I'm sure. But more seriously, I'm very impressed by the improvement of his knowledge in mechanical engineering, but not only. For example, in polymer materials also, I think I'm very impressed now. You know what is a polymer, we know how to, the influence of the viscosity. It's very important to take account this parameter for the field composite. So I would say now some words on Alexis. So he's how to say that? He's on a pen stacking worker. He's a very efficient people. This means that if you explain something to him one time, he will understand. But if you don't understand, you will work. He will work the necessary time to understand. So it's very a pleasure to work with him. And the last thing is a very nice person, and he's always enthusiastic. So so it's you know, we made a lot of meetings about thinking, and every time when I give him, he understands what I explain and he proposes a new solution. So it's a very good pleasure to work with you. I hope that I will continue to work with you.
Yeah, we will, of course, we will.
So you know that I plan.
I will not let you.
Yeah, you know that I plan to visit you next year. So I hope that the invitation will be better. So thank you for everything. Okay, congratulations for all the work you've done during the studies.
Thank you, Stefan.
Thank you very much. So now your second co-supervisor.
Thank you, President. I will be short. First of all, I would like to thank Diana, Christine, Eric, and Michel to the purpose of the show. Alexis, for many reasons, I am so happy also to be here today for continuing your events. Like the chairman to the Doctor said, what doesn't feel good makes you stronger. This last 3.5 years, including your master thesis, so in fact was effort. We can now measure the progress made starting in 2014-2015 with the crazy idea to print batteries with a 3D printer. It took like Stefan said, it took 2 years to convince the region in order to obtain financial support. but like retired researcher, founding team member of the lab Bernard ENSAIT, the best mushrooms do not grow up in the middle of the track. See where we are now. Because of you, we reach the proof of concept step.
Thanks to you.
Opening new doors to new academic and industrial collaboration, national and international ones, and to continue on the sound scientific basis researches on this topic. So, Alexis, it was a pleasure to work with you. If I have to define you in several words, I would say ambassador and bridge. Indeed, you play this role between labs such as LTI and LRCS, but also with our friends in Finland and with Eric. I really hope that you will be able to join his team in February, financed by a Fulbright grant, even if two calamities are presently exist and cannot be underestimated: the coronavirus and Donald Trump. Then you're also open-minded people. I think that is in your own being, and this character trait was reinforced by the 2 years you spent in the MESC Erasmus Mundus program. Last but not least, you are also a high-speed locomotive. Being three of us with Sylvie and Stefan to follow you was not too little. I would like to thank Sylvie, Stefan, and also Hugues to be part of this adventure which has started, and also Michel, who is playing the role of playing Docteur. Michel is like an electron. His presence probability around the world is equal to 1, but as soon as we need him, he is answering. So, Alexis, I'm sure that you are promised for a vibrant future, and that we will continue to collaborate wherever we will be on the planet or in space.
Yeah.
I'm wishing you all the best. Thank you.
Thank you very much, Greg.
Okay, so now it's time to conclude. So it's time for the deliberation. So can you leave this room just no? We move.
Yeah.
Okay, sorry. So we move.
We stay
and we come
here
back
with
just
the
after.
public, and we will wait.
Okay, thank you.
Tu m'enlèves de la salle, Louis. Oui. Oui. Tu mets en wiki. Tu mets en wiki.
Thank you.